Hi, today we'll be looking at Death Note. It's a 250 point challenge. So actually, uh, by the name of it, Tcache here will involve learning Tcache, and see the file will involve, I think, file structure exploitation, which I don't have any uh, background of. So I need to read those two before I could solve this challenge. I think at least this one Tcache is okay. I might be able to do it, but I'm short on time, so today, instead of explaining, we'll be trying Death Note. I don't know what sort of challenge is this, but my friend told me that mm, this should be easier than reading upon both of those two. So Death Note is x86, not stripped, dynamically linked. All right. So, but we don't have the libc provided here, so that might mean that we need to craft an attack. So it has no pi, it has canary, has RWX segments, so and NX is also disabled, so that might mean it can be pretty easy. Then we have partial railroad, which is okay. So let me open it in IDA. But then let's look at some symbols. So somebody told me that the size of font is a little too small. So what I'm gonna do is I'm gonna increase the font size for the stream. Let's say 28. Okay, I think this would look better on stream. People said that you're not utilizing the complete screen. So all right, uh, let's look at this directly. So we have a main is standard non-blocking input, non-streaming, I think. Then you have menu, add, show, delete, and exit. Then we have read int. So based on that, we have different add, show, delete, puts, valid choice. Here's exit, and it's an infinite loop. Yeah, so infinite loop, read integer. Very small code. So first we look at add. What add does is something index, and so let's name it index. So it takes index. If index is greater than 10, that is out of bound. All right. Then we give it a name. We can call it. Oops. And there's a check if is printable, which is char. I think 0x50. Let's change type. I think this should be enough. It reads 80 bytes, is printable based on the string length. It will check if it's less than 31, which okay. And that means it should be less than 126, and so this is the maximum possible positive char. Can't be less than 31. less than equal to, so it's not less than 32 and whatever. All right, so that means 32 is here, space, we can go from space to this. That means we have all the symbols, numbers, AB, capital and small. All right, that's okay. And then you do str_dup. I think str_dup mallocs and returns as a memory. That returns a pointer to new string which is duplicate of the string s. Memory for the string is obtained with malloc, can be freed. All right, so uh, we don't have a malloc import here. Instead we're using str_dup, so whatever input we provide, it will be checked. If the check passes, then malloc copy and note. This should be in BSS. All right, so note is void star note. All right, so after add, we can look at show. Same, you read index and then you directly just print f. And then we have del. So in delete we have index delete and out of bound. Then you free it, you set it to 0. So that removes the chances of use after free, and the pointer is set to 0. So that's pretty small code. But in this case, I think this index is an integer. So we might be able to read negative values. So if we go to the base of note, we might, instead of writing here, we can write at this side. So that gives us control over two file pointers. And the GOT table itself. So that should be pretty easy, I think. Let me check what sort of permissions do we have. We'll put that main, then we run. So our stack is rwx, heap. Oh no, BSS is rwx. Heap is not still initialized. Let's break at malloc. And let's say I'll go to this fin, and then right. Okay, so now our heap is set. This is the heap, it also has rwx. So whatever name we provide, so that directly goes into the rwx region, so that means it's executable. And we have a control of GOT, so that gives us a good primitive that will be able to overwrite over this entry, let's say str_dup or free or whatever, with a pointer which was returned from str_dup, which actually points to an rwx segment. So I think this should be pretty easy. So one constraint here is that when you do add, so when you add, there's this is printable check. So couple of options that we can do is some ASCII shellcodes are available online, so we can use that and directly solve it. Other than that, we can try to write a very small shellcode in ASCII that gives us that lets us take more input and then jump to that shellcode which will not be or like part of this check. So we have a couple of options. So since the first option is getting ASCII shellcode from the internet is quite easy, let's not do that. Instead, let's just try to write a small shellcode that will help us in getting code execution. And we want to write the smallest shellcode possible. So Pawn Tools has this great feature, call it ASM. What this does is it you can give it arbitrary x86 instructions and it will assemble it. And when used with dash D flag, you can even debug the instructions given. So let's say I say so by default is x86, so we don't have to provide context, but it's better if we do. So this is the context, and in this case we need to provide x86. Yeah, i386. So it will split into other GDB, which is the exact instruction that we provided here. And if we don't provide the dash D flag, it will print. You can verify. Oh, and hex doesn't work for some reason. Never mind. Oh, it automatically detects whether you are printing to std out or not. So that's good. So in this case, we can see it's x86 pop eax is 58. So apart from pop eax, pop all registers such as esp is also ASCII printable, and then what other we have is we have increase, which is ASCII printable. We have decrease, which is ASCII printable. I don't know what push, but yeah, push is also ASCII printable. So these are some simple instructions that are ASCII printable in this case. We can use these instructions to somehow do this. Now, one other ASCII instruction, I think this. Mm, so I have done this in some other CTF challenge of shellcoding ECX. Let's say I think this is ASCII printable. No, so if I do this, yeah. So this is also ASCII printable. XOR, dword pointer, ECX something, and EX. Other than this, we have subtract. That is also ASCII printable. We have add. Add is not ASCII printable. All right. So XOR and sub are okay. Apart from dword, we can also do byte. Oops. Instead of EX, it should be a low. Yeah, that is also ASCII printable. So using this exact instruction, we can write a self-modifying shellcode, which will modify parts of shellcode which follow this instruction. So that means after this instruction, and we'll be able to change bytes. So initially we provide some bytes which are ASCII printable, then we use such operation to change those bytes uh, into proper shellcode. So that is one strategy that I have used for earlier challenges. So in this case, we have, let's say, so we have a GOT entry that has, I think everyone is all right. We can even patch free, which is rarely called. We can patch strlen, that is also, let's look at strlen first. Free was only called once, and strlen I don't remember strlen. Yeah, okay, that is only being called once, so this is also a good target. We can also patch exit. In this case, exit will be only called once. We can trigger, we have trigger for that. So what I would like to do is I would like to patch strlen, because then when we jump to, when we patch entry of strlen and then we later uh, call strlen, this will be in our control. So that means apart from controlling data, we'll also have some control over the stack. At least first or second keyword on the stack will be pointed to input that we control. So we can use that to help our instructions here, like this. All right. So one thing that we can do is since let's look at this first. Ret is out of the printable region. We will try to craft ret instruction on this with the self modifying perimeter that I talked about earlier, and then we'll try to ret to this input that we'll be having as our first parameter to strlen. So what eventually that will give us, that will give us some control over the stack, uh, and we can write a small drop chain to get more input and jump to it. So let's first do that. Let's write a small shellcode that manipulates itself to get to ret. So let's see. First thing first is that ECX should contain the pointer to the current instruction or somewhere later. So we need to populate ECX with the EIP, and then later at 24 offset from there we'll be able to subtract or XOR or whatever. So in this case, um, I think we can use XOR. Yeah, XOR is also cool. So for I in range 255 to 256, we don't want it to be 1 2. Actually that input could be anything. Let's see, 256 print char of 0xC3 XOR I. Yeah, so in this case we can take any of this value. So let's say we take any value. Let's take this value. I think that will be better. So 130. So So 0x8 to XOR 0x C3 is this. So if we want to get C3, we write 41 by there like there earlier, and later then we XOR it with 82. Then that byte turns to C3. So we'll be using that. Other than this, somehow we need to populate address of ECX inside with the value of EIP or somehow close to EIP, so that we may be able to change it using increase decrease. So let me look for a leak. So at the first run we try to patch the address of str and got, and then we can later, so we have some pointers to got in this region too. No, this is the actual got in this region, so let's have a look at that. So for example, yeah, so in this case we have pointers to uh, the RW region from the R region, and we also have pointer to got here. So we know that at 804941C we will be able to read out from this show note. If we give it a negative index, we will be able to read that as a pointer. So that means if we patch strlen with in first attempt we patch strlen with the str2 entry, so heap address will be written here, and later we use this index to read, so that means we'll be able to leak that value. So I think I have some idea of what I want to achieve. Let's try to write a script. So context dot binary is slash mm, this, and what else? So s is equal to process slash tmp slash death note, and say gdb dot attach s with a breakpoint that we can set at is printable. All right, so once we have that, let's try to look at how the binary runs. Mm, so all right, so s dot, so send line after we can after colon we can send str of 1. That means I want to add a name. So in this the first attempt we try to override the entry, so I with the negative index. So in this case idx is equal to elf dot symbols, no, elf dot got. So I want to patch strlens got address with the, in this case you have the symbol note. So elf dot, so I think that index is good. Then we can say mm, once we have done that, let's say minus, no, 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 minus 1, let's say 0 and 1 0. We need to send in the content that or the code that changes into this. So s dot send line after name. So what I'm trying is we need ECX, we need EAX, and then we do XOR the word. Okay, I think we can leave this for now. Under ECX plus 0x24 with AL. And since there will be a return address here, we can pop that. We can do that twice. Alright, so we can verify. Oh my god. For now, we can debug over this. Knew that would happen. Okay, so why did I do dword? That's on me. we have a break on is printable. Right now, if you look at GOT, everything should be fine. We'll continue this and I'll try to add a new name at the same point. Now if we look at GOT, yeah, so we have control over strlen's address. PopECX, yeah, that is all right. So hmm. Now next time I try to leak this address. Okay, so yeah, this one. So now I want to leak. So to leak, we need to show. So show is all right. Need to recalculate index here. So idx is equal to this address minus this thing, then you divide it by 4. No, not 1 but 2. Hmm. To receive this, so unpack that value, leak, and I try to print it. And this will help us craft our third payload. So in the third try, what we do is using the leak that we have, we populate this value. So we call strlen, we populate this value and this value, and help us make this into ret, and we write all option in that input itself. So same. So this time uh, we try to do one again. and index can be anything, so that is all right. So now here what we want to send is to send leak plus the value of ex that we were trying. So in this case, we can send 0x82. Once we have 0x82, actually 82 is too much. We're going to send 0x41. This is ASCII. This is not limited to ASCII character, so we can kind of send anything here because the check has not been performed yet. So this XOR was 3 bytes, I think. Yeah, so this XOR is 3 bytes and 3 bytes for this. That means total 6 bytes we have utilized till now. We also need the actual part of pop ESP. That means we have utilized 7 bytes. So to achieve 0x24, I'm gonna do is I'm gonna write increase EBX into 0x24 times minus 7 bytes of these, and then I want to send this. So I think this should be good enough for this self-modifying thing. Alright, so this is the first call to is printable, and the second call. So right now we'll have our GOT address patched, so we can step into strlen and see what we're doing. So as this is the return address, and this is the first parameter that will be passed to strlen for calculating length. So here that is totally under our control. So we did a dummy pop to remove that. Then we pivoted our stack pointer, and now ECX contains address to the base of the shellcode, which can be verified here. Yeah, so this is the that part, and then we have pop ex. Now when we do tele $ECX plus 0x24, it should be a, but with execution of this instruction, one of them turns to C3. So now if we do /xi, it's actually ret. So now we can step, and we eventually hit ret. So since stack is completely in our control, we can use a small drop chain here, which gives us the full control. So to do that, let's write that drop chain. So in this case, what the drop chain should do is it should call read input. So read input I think takes 2 parameters. buffer and n bytes, so we can use uh, any region right now, because even our data section is executable. So I'm going to use the note itself. So we'll write a drop chain. So we call read input followed by the two parameters. So this one is the return instruction. We actually want to return to the code itself. So we are kind of trying to get into that input, and then we read 0x100 bytes, and then we send line shellcraft.sh. I think this should be enough. Okay. So right now we have read input on that address. Just gonna jump through. So now our, those the parameters passed to. Oh, we have not. Um, this parameter was all right. Oh shit! I missed a critical detail. So in this case, instead of sending this, need to send this actually to assemble the shellcode. And yeah, we do ls. All right, we don't need gdb. Oh no, sorry. So in this case, we have the shell. We can disable gdb. Now and do ls. Yeah. So this challenge is, I think, done. We can do it on remote, I think. This is equal to remote 10201. Yeah, so now we can call this. Okay, we're still running here. I don't think I've saved it. Yeah, we have shell cat home star flag. Shell code is so beautiful. All right, so this concludes our challenge. So let's have a small recap. We're given an x86 binary with a very small main function with only three features, I think: add, delete, and show note. So what the add does is it mallocs a small space, and it assigns to the note array based on your index, but that index took negative values, and that gave us arbitrary control over what we are writing. So we have control over what we are writing, but the pointer we can use this pointer to write anywhere on the data segment. So that region or that map or page on the memory also has the GOT entries. So we use this to patch the GOT entry of strlen. So there's an additional check in add that lets us only add printable characters. So we wrote a small printable shellcode that passes this check, and that gives us enough control so that we are able to get into level 2 of our attack in stage 2. What we do is we use the show node feature to leak the GOT entry that we patch, so thus leaking the address where our shellcode lies. So now we have the knowledge of where our shellcode is, and we wrote our shellcode in a way that with that knowledge we'll be able to modify the shellcode itself. So we use that to, in this case, uh, we use zor byte pointer something something, and pop, using wait. So in the third stage, what we finally do is, since we have control over GOT entry of strlen, and we also contain control what is passed as parameter to strlen. That means second d word on the stack, first d word will be the return address. So we use that to pivot the stack onto our input. So that means now the stack is in our control, and we can using push and pop will be able to populate arbitrary values in our registers. So using that we populate a value into our AL, which we zor with our old shellcode to finally make it red. And since we have control of the stack, we also write a small drop chain that reads more input here, that reads more input to some place on the data or BSS. We can even do it here itself, that reads and jumps to other address. That's it. So this was a pretty good challenge. uh, uh, Other thing that could be done is we can have um, an ASCII shellcode, a completely ASCII shellcode, and we can use it directly to finish this exploit in, I think in just a couple of lines. So that's it for today. Let's see you next time.